Okay, and what we've discussed so far, we haven't really mentioned the concept of type and types very much. But in fact, Haskell is what is called a strongly typed language. And what that means is that every valid expression and value that we use in Haskell has a type. And if there's an error in a type anywhere, then the compiler will find it and report it. And the idea that it's statically typed means that the types are checked at compile time, so that at compile time the types have to match, they all have to be well behaved and correct in order for you to be able to actually run the code. You can't run code which contains type errors. So this is to be compared with, for example, Java, which is also a statically typed language, in contrast to scripting languages such as JavaScript or Python, where types are checked dynamically and there's a lot of dynamic coercion between types so that the types can work even though they might not look like they can at first glance. Now that said, you may wonder then why you haven't seen any types. I mean, when you program in Java, for example, types are really in your face. And the reason for that is that Haskell supports something called type inference. Haskell works out what the types are of your examples on all your definitions and all the expressions in your definitions, and reports a type error if there are any errors in those. And so even though we don't necessarily always write type information, there is type information there. It's information that is inferred by Haskell. And in general, what Haskell will do, what the Haskell compiler will do, is to find the most general type that it can for a given expression. Now, in fact, even though there's no type information in this particular code that I've written, adding type information as part of your code is a good idea, in particular for top-level definitions, for a number of reasons. It helps document the code. By reading the types, you can understand a lot about what the code does. And it also helps understand when there are type errors, because when you declare a type, you declare what type you're intending your code to have. And that gives something for Haskell to compare against. And so what Haskell will do is infer a type and compare it with the type you've given. Now, the type that Haskell infers may be more general, but it should be compatible with the type that you give. Otherwise, there is a type error. And so generally, we will expect you to, and you should as good practice, when you've developed your code, either at an early stage or at some stage during the development, include type signatures for your code. So let me start by doing that for some of the examples we already looked at. Let's look at the exchange rate as one example. We can declare the type of the exchange rate, and we can say that, so we need to use one of the standard number types here. And on the left here, you see we have a list of some of the standard built-in types of Haskell. We've seen, for example, Boolean values, the values true and false. And there are two types of floating point number. They're called float and double. And float is just a floating point number of a certain precision, and double refers to double precision floating point number. So let's call this a double, just to choose something. So what I've done is now I've added a type declaration to my code. And I've said that exchange rate, this should be interpreted as a double. Now, if I don't do that, it will actually have a more general type than this, but I don't want to get into the details of more general types yet. So we'll just work with that for now. And now actually we can see that we can actually ask what is the type of the exchange rate. It is indeed a double. And we can also ask now what is the type of these functions. So from SEK, for example, we can ask the interpreter what type is from sec. And you see that from sec is a function, and this is the way that a function is written. It's a function of one argument. That argument is a double, and it returns a double. So we see the argument type is on the left. There is these two symbols, which you should think of as an arrow, the usual mathematical notation for a function space. And there's the result type. It is a double. So Haskell has inferred this type from the information that it has. And the information it has is that it has checked that this type is indeed compatible with what we wanted it to be, a double. So that's all fine. So that means this is a double. And so Haskell then infers that this result must be a double. This must also be a double. And therefore, this is a function from a double to a double. Now we can make that clearer in our finished code by inserting that specification. And I was actually just going to copy it from down here and insert it into our file, and we can do the same with the from GBP, from Great British Pounds, is also a function from double to double. Okay, what about prop exchange? What type do you think that has? Well, our intention is that the argument is something that can be passed to this function, so it must be a double. So this takes a double as an argument, so let's write that in. So the prop exchange has type double and returns as its result a double? No, actually not. So you can see this is actually just broken over 2 lines because I've shrunk my window. So this is actually all on the same line. The result is a Boolean value. It's a value like a true or a false, and those have type bool, short for Boolean. So this is a bool. So quick check tests functions which return, amongst other things of type bool. Okay, let's go down to our definition of the power function, because this one's a little bit different. It's different because it has 2 arguments. So it's useful to see how that will appear in the type. However, what was important about this, and why this is a good example where we would like to insert our own definition of a type, is because the type of power is not obvious. It's not completely obvious in the definition, or rather, when Haskell infers the type, it will infer a very general type, basically saying, well, for various combinations of different kinds of numbers, this will work. And we want to be a little bit more specific, so we're going to keep life simple for now. So we want to say that this is a function that takes an integer, another integer, and returns an integer. So our version of function will take 2 integers as arguments and return an integer. So let me just write the bit, the return type first. We know that that's going to be an integer. We want that to be an integer. But it has 2 arguments. So how do we write the types of those arguments? Well, we write them in the following way. The first argument is an integer, and the second argument is also an integer. Now this might look a little bit mystical at first. We're saying, so this, the thing on the far right, you can think of it as the type of the result. So this is taking an integer argument, another integer argument, and giving you an integer back. Now the reason why it's written in this way is that in fact we can use power in more ways than just providing it with 2 arguments. We provide it with 2 arguments, 2 integers, we get back an integer. What turns out that we'll see later when we talk about higher order functions is that we can also apply power to just 1 argument. And what do we get back when we apply it to 1 argument? Well, we get back something of this type, namely a function. And that's something called currying. So we'll talk more about that in around lecture 3, I think it is. But for now, just think of this as this is a function of 2 arguments returning this type of result. Let's just compile that again, just to check that we haven't made any mistakes along the way. And indeed we haven't, we get no complaints. Okay, so what other kinds of types are there? Well, we've seen Booleans, true and false. And we've seen integers, they're the ones we've just used, they're the whole numbers. And there is also another type, int. Now what's the difference between int and integer? So integer refers to the mathematical integers, roughly speaking. They can be very, very, very big. Int, on the other hand, refers to sort of computer integers of a fixed, bounded size. And so there'll be a kind of maximum int. So ints are good when we're dealing with smallish numbers. When we're looking at, for example, small ranges, then there's no danger that we will overflow. And that will be a more efficient representation for computations of small things, but not a suitable for example, the power function, which is by its very nature going to compute an exponentiation, very quickly creates very large things. So int would be a very poor choice for the power function. And we've also seen that we can have double precision floating points, they're called double, and then single precision floating points are called float. And then there's a couple of other things. We've seen strings. We used a couple of quick examples of strings. So here's an example of 3 values of type string, and they are typically written in double quotes. And control characters are escaped using a backslash. So that's the new line character that is embedded in that string. And then there's also individual characters, which is a distinct type from strings, and they're written in single quotes. And of course, the thing that you write in a single quote has to be a single character. So for example, it can't be 2 characters, because that would be not a valid piece of syntax. But a single character indeed is perfectly fine. It's just a character, char. Okay, now's a great time to talk about some other kinds of types, and some important ones, namely collections of things. When you want to deal with collections of things, there's basically 2 standard built-in types that are useful. The first are tuples or tuples, depending on how you like to pronounce it. There's no right way there. And that's for collecting a fixed number of things where the things you're collecting together into a single value have possibly different types. So for example, we might collect a bool and an int together to form a pair. That's a tuple of size 2. And the type of that tuple would be bool, int. So what you notice here is that the language for defining the types is the same as the language for actually defining the values. Now the size of the tuples can be as big as you like, but it's a fixed size for a given type. So the type reflects the types of each of the components in the tuple. Okay. Let's define a little function just to illustrate tuples. So we're talking about types, and let's define something to do with tuples. So let's define an example function which takes an integer. So we're going to write the type first. We're going to take an integer and return a pair of things, a boolean, which tells you whether it's negative or not, and the absolute value of that integer. So I'm going to call it ex1, and it's going to have this type. It's going to take an integer argument and return a pair of things. So ex1 applied to some number n is going to be equal to, we're going to give the answer true if n is negative, and the answer false otherwise for the first component. So what we're basically doing is returning whether n is less than 0. And that will give us true if n is less than 0 and false otherwise. And the second component will be the absolute value of n. So there's a little example of a function which produces a tuple, a pair. Tuples of size 2 are called pairs for obvious reasons. So if we apply that to -10, then it says true, yes, it is a boolean, and the value is 10. Okay, it's not a very interesting example. You might also wonder how you not only put tuples together, that's the easy part, using brackets and commas, but how you take them apart. Now there are some basic functions for doing that. In the case of pairs, there are built-in functions first and second, but for other size tuples, there are not there aren't equivalent functions for every size of tuple. I can just illustrate that. If I take the first of this thing here that I just computed, then that gives the first component of that pair. And then the other one is the second, sund, first and sund of that thing. We'll give the second part of it. But how might they be defined? Well, they're defined in the prelude, but if we were to define them ourselves, we would do so using pattern matching. In other words, we would use a pattern on the left-hand side of the defining equation. We would say that the first of something of the form xy would be equal to the x. So this is pattern matching. We're using a kind of pattern which is describing the shape of the argument and giving names to the pieces inside that shape. So this is a function which will take a pair of things and return the first of those. And the second function will be, of course, similar to that. Will be just y. So that's how we build tuples, and this is how we take them apart, typically using pattern matching. Okay, I'll comment these out because they are, of course, predefined functions. We don't need them here and now.